Hello, my name is Dr. Catherine Bradshaw, and I am from the Met Office and the University of Exeter in the UK. I am presenting work conducted in collaboration with fellow researchers at the Met Office, the University of Cambridge, CIMMYT, and the Ethiopian Institute of Agricultural Research. Stem rust is considered the most damaging of all the wheat rusts, and it has caused devastating epidemics in all wheat-growing continents. In sub-Saharan Africa, severe epidemic losses can be close to 100%. And after many decades of control, stem rust is now re-emerging as a disease of concern. Diverse new races and lineages are now being detected, and large outbreaks of disease are increasing. Ethiopia is the largest wheat-producing country in sub-Saharan Africa, where cultivation is concentrated in the central highlands under rain-fed conditions. But there has been a large increase in recent years in the area of irrigated wheat. The East African highlands are a hotspot for stem rust because favorable environmental conditions permit the pathogen to survive year-round. But equally important is the presence of host plants. Overlapping cropping seasons and bimodal rain patterns in most East African countries result in green bridges that facilitate the survival and buildup of inoculum between successive crops. Shifts from rain-fed to irrigated wheat further enhance the green bridge effect by extending wheat crop cultivation. From its initial detection in Uganda in 1998, UG99 race TTK-SK took 5 years before detection in Ethiopia and 9 years before detection in Iran. In contrast, a new race, TTK-TT, was first detected in Kenya in 2014, and then in Ethiopia 4 years later in 2018. And then in Iraq in 2019, just 1 year later than that. Race TTK-TT is now the second UG99 variant to move into the major wheat-growing regions of the Middle East, indicating a possible common migration route. In this study, we assessed the likely spread of this new race within East Africa and whether the detection in Iraq in 2019 could have originated by direct wind dispersal from infected sites in East Africa during the previous year, or whether intermediate stepping stone sites would be required. We use the atmospheric dispersion model NAME, driven by data from the UK Met Office numerical weather prediction model. The NAME model has been adapted to simulate the release, turbulent dispersal, wet and dry deposition, and UV-induced death of stem rust fungal spores. Sites are considered to be donors when the spores are dispersed from infected wheat, and receptors when spores land on susceptible wheat. Among donor and receptor sites, we distinguish between confirmed disease locations, in which the new variant has been confirmed, and representative disease locations, where the new variant has not been confirmed, but where stem rust is known to occur. Each site characterizes the broad wheat production region of the area. We use a simple SEER epidemiological framework operating on a daily time step to classify the infection status of the sites. A site moves into the susceptible class after a period of initial growth. Infected sites move into the exposed class, where they undergo a latency period before being able to affect other sites. The site remains infectious until leaf senescence prevents further spore production, when it then moves into the removed class. Sites that pass into the removed class are not passed back into the susceptible class within the same cropping season, because we haven't defined the length of the infectious period, and we don't allow for chemical control in our model. A meteorology-driven environmental suitability model is used to assess whether temperature and moisture conditions are suitable for infection when spores land on a susceptible site. Infected receptors remain in the exposed class until a crop latency period, the time between being infected and themselves then becoming infectious donors, has passed. The default version uses a temperature-dependent latency period based on the model of Nopsa and Fender 2014. And a second version using a fixed latency period of 30 days was examined as a sensitivity test. The integrated model allows a user-defined threshold for the combined environmental suitability and spore deposition value, above which a potential receptor becomes infected. In our study, we have assumed any value over 0 to imply infection. The first scenario that we tested was just the sites with confirmed identification of the new variant. Initial donors were assumed to be CDLs in Kenya, Tanzania, or Rwanda, shown in the map in yellow triangles. Under this scenario, the results show no transmission pathway between CDLs in East Africa and the Middle East in the 2018-19 season. We find that Tanzanian donors can only infect Rwanda, and spores released from Rwanda cause no onward transmission. Kenyan donors can infect all Ethiopian CDLs, but no onward transmission to Iraq is simulated. This means that other potential locations for wheat stem rust, where the new variant has not been identified, must be considered as potential stepping stones. The second scenario, given that we find spores from Rwanda and the 2 Tanzanian CDLs cannot infect any other CDLs, only assume the original infection from Kenya, because it's highly unlikely that Rwanda and Tanzania were the original origin of the TTK-TT infection in Ethiopia in 2018, or the TTK-TT infection in Iraq in 2019. For the next scenario, as well as these confirmed disease locations, we now also include sites in additional key wheat-growing regions in Ethiopia, where stem rust is known to occur, but the new variant has not been confirmed. These are an RDL in barley, an area of double cropping, and 2 irrigated sites along the Awash River Valley, Metahara and Wera. Inclusion of the additional RDLs results in infection at those sites, but the infection does not reach Iraq. This means that other potential RDLs in key wheat-growing regions in other countries where the new variant has not been identified must be considered as possible stepping stones to the Middle East. For the final scenario then, barley, Metahara, and Wera are again included, along with other possible stepping stone locations in Eritrea, Yemen, Saudi Arabia, and Iran. Each potential stepping stone country is considered individually, and in each case, we consider the results both with and without Metahara and Wera, the 2 newly irrigated RDLs in Ethiopia. In all cases, when Metahara and Wera are excluded from the analysis, the crop is harvested before the infection reaches Iraq. When they are included, stepping stone locations in either Saudi Arabia or Yemen are necessary to facilitate infection in Iraq. Focusing first on Yemen, we can see that in panel A, the CDLs in Ethiopia become infected in August 2018. But although the area of double cropping is infected in December 2018 in panel B, the infection dies out when these crops are harvested. When we include Metahara and Wera, the area of double cropping is able to infect these locations, as shown in panels B and C. And these locations are then able to infect East Yemen, and East Yemen infects Iraq in 2019, shown in panel D. Similarly, focusing on Saudi Arabia, the same situation arises as for Yemen, whereby no infection occurs when Metahara and Wera are excluded. But when they are included, they become infected in December 18 and go on to infect the Al-Kaj site in Saudi Arabia in February 2019, as shown in panel C. And then this infects other Saudi sites and the site in Iraq in 2019, as shown in panel D. We find, however, that infection of Iraq from spores released from East Yemen can only happen on 3 days in March and a single day in April 2019. Conversely, infection of Iraq from spores released from Saudi Arabia can happen on 29 days between February and April 2019, and therefore we consider the route through Saudi Arabia to be more likely. The sensitivity tests conducted revealed that the simulations using the 30-day latency period instead of the temperature-based model only create a viable pathway to the Middle East through Saudi Arabia. This is also the only viable route when we increase the probability of infection threshold above 0, and it itself ceases to become a viable route when the threshold is raised above 0.1. Delaying the date that sites can first become susceptible to stem rust by 1 month does not allow Metahara or Wera to be infected. The sensitivity tests therefore confirm that it is not just the overlap in the crop calendar that is important in creating the green bridge between East Africa and the Middle East, but also the fact that those RDLs are irrigated. So in summary, here I'm showing the confirmed disease locations in this schematic in orange and the representative disease locations in blue. The schematic shows that excluding Metahara and Wera only leads to infection of sites in Ethiopia and Yemen. When they are included, we find evidence that a disease outbreak originating in Kenya could reach Iraq in 1 year via stepping stone locations in Ethiopia, Yemen, and Saudi Arabia. However, the presence of irrigated wheat in those locations appears to be critical for spread. And finally, including the areas of double cropping allows reinfection of sites in East Africa, which could potentially repeat the cycle the following year. To finish, some implications from our work. Firstly, the results suggest that the transmission pathways are a low probability event, which means that targeted control measures could be used to reduce the risk. Increased surveillance in Yemen and Saudi Arabia should be a priority. Irrigation is increasing as an adaptation option to the impacts of climate change and to improve food security in many countries. Irrigation expansion plans should therefore include risk assessments to identify mitigations that may also be required. Mitigation strategies include the use of targeted fungicide, the use of resistant wheat varieties, and the use of appropriate irrigation systems. Lastly, early warning systems will be crucial for some of these mitigation strategies to work. Thank you.